In our expanding range of videos, here's some on Python and its challenges. As we know, Python is a versatile and widely used programming language, but like any language, it has its challenges, especially when it comes to advanced coding. In this video I'm going to explain 5 significant challenges that developers might face, and how to overcome them. First we have concurrency and parallelism. Python's Global Interpreter Lock or GIL makes true multi-threading difficult, as it allows only one thread to execute Python bytecode at a time. This can be a bottleneck for CPU-bound tasks. Writing concurrent and parallel code requires careful design to avoid race conditions, deadlocks, and other synchronization issues. Here's some non-optimized code for a function that computes the factorial of a number, and we want to compute the factorial of several numbers concurrently. In this code, we're using Python's threading module to create a thread for each number's factorial computation. However, due to Python's GIL, this code won't run the threads truly concurrently on multiple CPU cores. The GIL ensures that only one thread executes Python bytecode at a time, so the threads are essentially running sequentially. Let's optimize it. To optimize the code for true concurrency, we can use the multiprocessing module, which creates separate processes for each task, bypassing the GIL. Let's look at the changes made. Firstly, we replace the threading module with the multiprocessing module. And then we used a pool to manage the processes and the map method to apply the factorial function to the numbers concurrently. So what's the impact of these changes? The optimized code runs the factorial computations truly concurrently on multiple CPU cores, taking advantage of multi-core processors. By running the computations concurrently, the optimized code can complete the task faster, especially for large datasets or computationally intensive tasks. The multiprocessing module's pool and map method provide a higher level, more straightforward way to parallelize the code, making it easier to write and maintain. The optimized code leverages the power of multi-core processors to run the computations concurrently, leading to potential performance improvements. It also simplifies the code by abstracting the process management, making it more robust and maintainable. This is just a simple example, but it shows how to approach concurrency in Python. In this example, we are going to look at memory management and performance. Python's dynamic typing and garbage collection can lead to inefficient memory usage and slower execution compared to statically typed, compiled languages, and optimizing Python code for performance can be challenging, especially when working with large datasets or real-time processing. Let's have a look at an example. Suppose we have a large dataset of user records, and we want to filter users based on certain criteria, transform the data, and compute some statistics. Here's a non-optimized version. We can optimize the code by using generator expressions and combining the filtering, transformation, and computation steps into a single loop. So, what changes did we make? Combined the filtering, transformation, and computation steps into a single loop. Replaced list comprehensions with a for loop and conditional statements. Used a running total for age and count to compute the average age, avoiding an intermediate list. Let's have a look at the impact of changes. The optimized code avoids creating intermediate lists, reducing memory consumption. By combining the steps and avoiding unnecessary data structures, the optimized code can be faster, especially for large datasets. The optimized code clearly expresses the filtering, transformation, and computation steps, making it easier to understand and maintain. Integrating Python with C and C++ libraries can be a complex task, and managing memory and data types between the two languages requires careful attention. Let's explore an example that demonstrates this challenge and how to optimize it. Let's have a look at an example. Suppose we have a C function that computes the sum of an array of integers. We want to call this function from Python using the C types library. Compile the C code to a shared library. Now the non-optimized Python code. Here's a 5-second pause for you to press pause and view the code. Now here's the optimized version. We can optimize the code by using Python, a programming language that makes writing C extensions for Python as easy as Python itself. Here the Python code, which we compile ready for Python. So, what changes did we make? Replace the use of C types with Python, which provides a more natural way to interface with C code. Defined the C function in a Python file and created a Python wrapper function to call it. Let's have a look at the impact of changes. Python provides a more Pythonic way to interface with C code, making the code easier to write and maintain. Python can generate more efficient code for calling C functions, potentially improving performance. Python allows for more natural type declarations and conversions between Python and C types, reducing the risk of type errors. Python handles memory management more transparently, reducing the risk of memory leaks or other memory-related errors. Let's explore an example that demonstrates the challenges of type safety and static analysis in Python, and how we can optimize the code to address these challenges. Suppose we have a function that takes two arguments and returns their sum. Without type annotations, we have no way to enforce that the arguments are numbers, leading to potential runtime errors. In this non-optimized code, calling add 5, 10 will raise a type error at runtime because we're trying to add an integer and a string. Without type annotations, this error is not caught during development. We can optimize the code by adding type annotations and using a tool like MyPy to perform static type checking. This allows us to catch type errors during development, rather than at runtime. By running MyPy on this code, we can catch any type errors before running the code. For example, if we try to call add 5, 10, MyPy will report a type error. What changes were made? Added type annotations to the function signature, specifying that the arguments a and b must be either integers or floats. Use the typing module to define a type union, allowing for multiple valid types. What are the impact of the changes? The optimized code enforces that the arguments to the add function must be numbers, catching any type errors during development rather than at runtime. Type annotations make the code more self-documenting, clearly expressing the expected types of the arguments and return value. By catching type errors early, the optimized code is more robust and easier to maintain, especially in a large codebase. The optimized code leverages Python's type annotations and a static type checker like MyPy to enforce type safety, improving the code's readability, robustness, and maintainability. It demonstrates how careful attention to type safety can lead to more effective and error-free code, especially in complex or large-scale projects. Deployment and distribution of Python applications can be challenging, especially when dealing with dependencies, platform-specific issues, and the need to create standalone executables. Let's explore an example and how to optimize it. Suppose you have a Python application with several dependencies, and you want to distribute it to users who may not have Python or the required libraries installed. A non-optimized approach might involve providing the source code and a requirements.txt file, expecting users to install Python and the dependencies themselves. Users would need to install Python. Then run pip install and call the requirements.txt file to install dependencies. And finally, run python app.py to start the application. This approach is not user-friendly and can lead to issues with library compatibility, system dependencies, and platform-specific quirks. An optimized approach would involve packaging the application into a standalone executable or container, including all dependencies, and providing a simple way to run it. Using PyInstaller to create a standalone executable. Then we use Docker to create a containerized application. So what changes were made? Replaced manual installation instructions with automated packaging using PyInstaller or Docker. Included all dependencies and system-specific configurations in the standalone executable or container. Impact of changes? The optimized deployment provides a simple way for users to run the application without manual installation of dependencies. By including all dependencies and configurations, the optimized deployment reduces the risk of compatibility issues across different systems and platforms. Packaging the application into a standalone executable or container makes it easier to manage, update, and distribute, especially in complex or large-scale deployments. The optimized deployment leverages tools like PyInstaller and Docker to package the Python application into a user-friendly, compatible, and maintainable form. It demonstrates how careful attention to deployment and distribution can lead to a more effective and robust solution, especially when dealing with diverse environments and complex dependencies.